So moving right along, we're now into section 7.3, which is dealing with operations on radicals. Okay, so in 5 and 6 here, we're dealing with adding and subtracting radicals. Actually, the examples only have addition in them, right? But one of the U-triads has subtraction in it also. But it's essentially the same thing. Because remember, subtraction is really just addition of the opposite. So what do we do here? When we add or subtract radical expressions, we're essentially combining like terms. That's really what it's like. It's just like combining like terms was, right? With polynomials. Only terms containing like radicals, I'm going to call them, can be combined. So when combining like radicals, just add or subtract the coefficients and leave the radical part unchanged, right? It's just like when you would add polynomial terms, you would only combine the like terms, right? So like x's and x's, x squareds and x squareds, x cubes and x cubes. It's the same idea here, okay? So we're just going to add or subtract the coefficients, the numbers out front, and then leave the radicals unchanged. And of course, sometimes you're going to need to first simplify radicals in order to make them like, right? They might not be like in the form that they're given to you. You might have to change them into a form so that they are like, right? And that's actually the case with number 5 here, right? Example 5, we have the square root of 2 plus the square root of 18 plus the square root of 32, which of course none of them are like, right? Because one of them is a radical 2, one's a radical 18, and one's a radical 32. Okay, now radical 2 can't be broken down any further, right? It's just the square root of 2. But the square root of 18 can be broken down, right? We can write the square root of 18 actually as the square root of 9 times the square root of 2, right? So that's going to simplify. And the square root of 32 we can write as, right? So you might say 4 and 8, right? Because 4 is a perfect square, but there's actually a bigger perfect square that'll go into 32, and that would be 16. So we can write it as the square root of 16 times the square root of 2, right? So we have the square root of 2 plus the square root of 9 times the square root of 2 plus the square root of 16 times the square root of 2. And now, of course, the square root of 9 is just 3, and the square root of 16 is just 4. So this is really the square root of 2 plus 3 times the square root of 2 plus 4 times the square root of 2. And now we can see that they're all like radicals, right? That's kind of a term that I just made up. I don't think it's widely used. That's why I put it in quotation marks there, like radicals. They're all like because they all have the square root of 2 tacked on to the end of them, right? So this is like a 1 radical 2 plus 3 radical 2 plus 4 radical 2. So we just add them like we're combining like terms. 1 plus 3 plus 4 is 8. So we have 8 times the square root of 2, right? Or 8 radical 2, right? Some people will say 8 times the square root of 2. Some people say 8 radical 2. Or 8 square roots of 2, some people say, right? But either way, it's just the same thing. Okay, so there we go. So that one they were all like. All right, now at number 6, we can see that we have a 3 square root of 2 and 7 square root of 5, which are not going to be able to be broken down any further. Okay, and they're not like, so we know not all of these are going to combine already. But now the square root of 20 can be broken down. I think we broke down the square root of 20 in example 3 or something, or example 4. So the square root of 20 is really the square root of 4 times the square root of 5. So, and after you do these enough, you can kind of skip this step here that I'm doing and just write this as 2 square root of 5. But we're still pretty new at this, so I'm going to actually show all the steps here. So I'm writing the square root of 20 as the square root of 4 times the square root of 5, but I still have this 2 out front. And now I'm adding that to 3 square root of 2, and then I'm adding that to 7 square root of 5, right? And now 2 times the square root of 4 times the square root of 5 is really 2 times 2. And again, I'm showing all the steps here. Some of these steps could be skipped. So all I did right there is replace the square root of 4 with 2, and now 2 times 2 becomes 4 square root of 5 plus 3 square root of 2, which are not like, so they're not going to combine, plus 7 square root of 5. And of course, the 4 square root of 5 and the 7 square root of 5 are like radicals, right? So they're going to combine. 4 and 7 is 11. So this just becomes 11 square root of 5 plus 3 square root of 2. And that would be your simplified answer there. 11 radical 5 plus 3 radical 2. Now the final topic in this section 7.3 is something that actually some of you brought up when we did the section on the trig, when we were getting things like the sine of 60 degrees is the square root of 3 over 2. Actually, no, that wouldn't be 1. Sorry. When we were getting things like the sine of 45 degrees is 1 over the square root of 2, people were asking me, well, do you want us to rationalize the denominator? And I said no. At that point, we didn't have to because we hadn't done rationalizing the denominators yet. Okay? So what is rationalizing denominators? Basically, it just means you're trying to remove radicals, right, square roots, cube roots, from the denominator of an expression. That's what you're trying to do when you rationalize a denominator. All right? So, in general, how will you do this? You can generally you want to multiply the numerator and denominator by something that'll eliminate the radical, right? I mean, that's kind of clear, right? Because if you have an expression like this that's a fraction, the only way you can legally change it is by multiplying it by a form of 1, which would be something over itself. So you're going to multiply by some expression over itself that'll eliminate the radical. So in 7, you can see here we have this first scenario, right? The expression is a single term. Actually, you can multiply by the expression itself, or a power of itself, if it's, a cube root or a fourth root or something like that. But generally, we're going to stick with square roots here for the most part. So you have 5 over 3 times the square root of 5. So the thing I want to eliminate is the square root of 5, right? I'm trying to eliminate this square root of 5 from the denominator. So how can I do that? Well, if I multiply the square root of 5 by itself, the square root of 5 times itself is just going to give me 5, right? Because it's really the square root of 25, which becomes 5. But again, remember, if you multiply the denominator by the square root of 5, you've got to multiply also the numerator by the square root of 5, right? So the numerator, and that's like the trade-off here, because what happens is, okay, sure, I eliminated the radical from the denominator, but in multiplying by the square root of 5, now I introduced a radical into the numerator, right? So the numerator is 5 square root of 5, and the denominator is actually going to be 3 times 5, which is just going to be 15, right? So this is really 5 square root of 5 over 15. And now you want to simplify it if you can, and of course you can simplify it because 5 over 15 is really 1 over 3. So this thing just simplifies to the square root of 5 over 3. And that would be your solution, right? That would be your simplified result with a rationalized denominator, the square root of 5 over 3. Okay? So you want to multiply the top and bottom by the square root of 5, because the square root of 5 times itself is just 5. Right? Now, I actually could have skipped that middle step where I multiplied 3 by 5 if I had seen in this first step that, ooh, look, 5 over 5 cancels out. So I could have went directly from this first step to the end if I had seen that. Right? I actually did see it. I just wanted to go through the process. Right? So that was if you have a single term in the denominator. Okay. Now, what happens if the expression is 2 terms, like it is in number 8? You have to multiply by the conjugate of the expression. Okay. And what does that word there mean, conjugate? Well, the conjugate of a plus b is a minus b, and vice versa. So the conjugate of a minus b would be a plus b. So basically, you're just changing the sign. You're leaving the expression unchanged, you're just changing the sign. Okay? So here our denominator is the square root of 5 plus the square root of 2. So that's like a plus b. So the conjugate of a plus b, we said, is a minus b. So the square root of 5 plus the square root of 2, multiplied by the conjugate, it would be the square root of 5 minus the square root of 2. And again, I do it in the denominator. I also have to do it in the numerator. So I multiply the numerator and denominator by the square root of 5 minus the square root of 2. And the numerator, realistically, you can just leave it in the factored form if you wish. You can just leave it as the square root of 2 times the square root of 5 minus the the square root of 2. It's up to you. You could actually multiply it out. You'd have the square root of 10 minus 2 if you wanted to, but either way, it's fine. So I would leave that in factored form. And now the denominator, the idea of multiplying by the conjugate is, technically, it would be a FOIL problem, right? But being that you multiply by the conjugate, you did that strategically. So then the O and the I of FOIL will cancel each other out, right? The OI of FOIL, as I like to call it, will cancel out. And then you'll just end up with F and L, right? So in this case, the F would be the square root of 5 times the square root of 5, which is just going to be 5. And then the L is going to be the square root of 2 times negative square root of 2, so it's going to be minus, and the square root of 2 times itself is just 2. So you see how beautiful that is? We've eliminated our radicals from the denominator, and now our denominator is just a single number, 3. So again, I'll leave the numerator of the mess that it is. It's the square root of 2 times the square root of 5 minus the square root of 2, and it's all over 3. Okay? So again, like I say, it's a trade-off. In making the denominator free of radicals, I've now introduced radicals into, well, it already had a radical, the numerator, but I've introduced more radicals into the numerator, right? So like I say, it's a trade-off. You get rid of it in one place, but you're adding to it in the other place.